All right, today we're going to be code breakers, but we're not cracking some digital password. Nope. The code we're after is written in wires, resistors, and batteries. We are going to find the master keys that unlock the secrets of pretty much any electrical circuit, no matter how complicated it looks. Okay, so let's just jump right in. Take a look at this thing. Seriously. It's got more than one power source, a bunch of different loops. I mean, it's a total maze. Where would you even start if you wanted to know how much current is flowing through just one of those wires? It looks pretty intimidating, right?
Now, if you're thinking Ohm's law, voltage equals current times resistance, that's a great instinct. But for a circuit like this one, you're going to hit a wall, and fast. Ohm's law is perfect for simple stuff, but here, it's just not going to cut it. We need something way more powerful.
So, to get over that wall, we have to upgrade our toolkit. That's what this is all about. We're going to level up our circuit-solving game and get way beyond the basics. You can think of it like this. Simple circuits are like basic door locks, but the complex ones, they're like these high-security bank vaults. And to get inside those, you can't just jiggle any old key in the lock. You need the master keys, a set of rules that can open any door, no matter how many locks it has. And you know what? Those master keys actually have a name: Kirchhoff's laws. There are two of them, and once you have them, you have the fundamental toolkit for analyzing pretty much any circuit. These are the heroes of our story today. Let's check out our first master key, Kirchhoff's current law, or KCL for short. The amazing thing about this law is just how simple it is. It really just boils down to one single idea. Whatever electricity flows into a junction, a point where wires meet, the exact same amount has to flow out. It's all based on this fundamental rule that you can't create or destroy charge. Yet people call it the junction rule. Just imagine water pipes all meeting at a single point. You can't have water just disappearing at the connection, right? All the water flowing in has to equal all the water flowing out. Well, electricity is the exact same. The charge doesn't just vanish. Okay, so our second master key is all about energy. It's called Kirchhoff's voltage law, or KBL. This one says that if you follow any complete circle or loop in a circuit, all the voltage boosts you get from things like batteries have to be perfectly canceled out by all the voltage drops you get from things like resistors. We call this the loop rule, and it's just a beautiful way of looking at the conservation of energy. Think of it like being on a roller coaster. The battery is the big hill at the beginning. It lifts you up, giving you a big voltage gain. Then, as you zip around the track, every twist and turn through a resistor is like a little dip, a voltage drop. But here's the thing. No matter what crazy path you take, when you pull back into the station, you're right back at the same height you started. The total change in your height, your energy, is zero. So, we've got our two master keys, the current law and the voltage law. Now for the fun part. Let's go back to that monster of a circuit from the beginning and actually use these keys to crack its code, one step at a time. Here's our game plan. It's a pretty straightforward four-step method. First, we'll map out the important spots, the junctions and the loops. Second, we'll just guess which way the currents are flowing. Third, we use our new master keys to write out some equations. And fourth, we just solve them. See? It turns this messy visual puzzle into some clean, manageable algebra.
Okay, let's get to it. Step 1, find the junctions. These are just the points where the wires split. So we've got one here and one here. Then we need to pick our loops. We need to make sure every part of the circuit is in at least one loop. So let's take this one on the left and this one on the right. Perfect. Step 2, assign directions to the currents. Now here's the best part. Don't worry about getting the direction right. Just pick one. Seriously. If you guess wrong, the math will sort it all out for you. You'll just get a negative number at the end, which means, oops, the current is actually flowing the other way. It's basically foolproof. All right, on to step 3, applying the laws. Let's trace our first loop together. As we walk around the loop, every time we cross a battery from the negative side to the positive side, that's a voltage gain. We add that to our equation. Every time we cross a resistor going in the same direction as our arrow, that's a voltage drop. We subtract that. We just do that for the entire loop, set the whole thing to equal 0, and boom, we have our first equation. And then, well, we just do the exact same thing for the second loop. We trace the path, add up the gains, subtract the drops, and bam, we've got our second equation. It's just a system. But wait, we still have too many unknown currents for the number of equations we have. That's where our first master key, the junction rule, comes back to save the day. We apply it to one of our junctions. Current in equals current out.
And just like that, we have a complete set of equations. Now, the physics is over. This isn't an electronics problem anymore. It's just a classic algebra problem, ready for us to solve.
So we do the algebra, and out pops the answer. For example, we might find out that the current in this one branch is exactly 1.5 amps. And that's it. That's the aha moment. By using these laws, we took this tangled mess of wires that looked impossible and turned it into a completely solvable puzzle. The code is officially cracked.
But look, solving one little circuit is just the start. The real magic of Kirchhoff's laws is just how universal they are. So, are they the perfect tool for everything? Well, the huge advantage is that they work for any circuit, period. The limitation, if you have a circuit with, say, 10 loops, well, you're going to end up with a massive system of equations that's a real pain to solve by hand. But the laws themselves, they always hold true. And why should you care about any of this? Because these aren't just some abstract rules in a textbook. These are the fundamental laws that make the electronics in your phone work. They're what makes the computer you're watching this on tick. They govern the gigantic power grids that light up our entire world. These laws are running silently in the background of all of modern life. So we've seen how these laws are the master keys to unlocking our entire electronic world. But it does leave you with a pretty cool question, doesn't it? These rules perfectly describe how charge flows on our scale, but what happens when you zoom way down to the quantum level, to a single electron? Do these same rules even apply?